The ocean's salinity is a story of epic scale, formed over millions of years by a multitude of natural forces working together. It's incredible to realize that the salty taste we associate with ocean water is a result of 50 quadrillion tons of dissolved salts circulating through our seas today. That's 50 quadrillion tons, enough salt to form a layer almost 500 feet thick over the entire Earth's surface. But where did all this salt come from, and is the ocean getting saltier? Let's dive into the main processes that created this vast reservoir of salt. For billions of years, rain has fallen on continents, eroding rocks through a process called chemical weathering. This weathering breaks down minerals, which then release ions like sodium and chloride, the key components of salt. Through rivers, approximately 4 billion tons of dissolved salts flow into the ocean each year. Although rivers seem fresh to us, they carry trace amounts of these minerals that accumulate in the ocean, continuously adding to its salinity. But rivers aren't the whole story. Under the ocean, a hidden process called hydrothermal venting contributes significantly to ocean salinity. Deep-sea vents and underwater volcanic activity release large quantities of minerals, including sulfur, magnesium, and calcium, which further enrich the seawater. Hydrothermal vents operate at depths where seawater meets magma in the Earth's crust, reaching temperatures up to 400 degrees Celsius, 752 degrees Fahrenheit. This interaction causes seawater to undergo chemical transformations, contributing not just salts but also metals and gases that nourish unique deep-sea ecosystems. These vents play an essential role in maintaining the ocean's mineral balance by cycling various elements back into the water column. Considering the annual addition of 4 billion tons of salt, it seems like ocean salinity should be rapidly increasing, right? Yet, the salinity levels have remained relatively stable over recent geological timescales, averaging around 3.5% or 35 parts per thousand. This stability is due to natural balancing mechanisms, one of the most significant being sedimentation. Over time, certain salts and minerals precipitate out and settle on the ocean floor, where they accumulate in sedimentary layers. This sedimentation acts as a natural buffer, preventing excessive increases in salinity that could disrupt marine life. Interestingly, the rate of sedimentation has its limits and is sensitive to factors such as ocean temperature, pressure, and biological activity. In warmer climates, for example, evaporation increases, concentrating salts in the water. Regions like the Red Sea exhibit higher salinity, reaching 40 parts per thousand or more, due to high evaporation rates and limited freshwater inflow. Conversely, areas near large freshwater inputs, like the Amazon River, show lower salinity levels, creating local variations in ocean composition. This fine balance of salts in the ocean plays a critical role in marine ecosystems. Salinity affects osmoregulation in marine organisms, dictating their ability to maintain fluid balance. Many species have adapted to specific salinity ranges, so even slight shifts can disrupt ecosystems. For example, if salinity increases significantly, it can place stress on fish, coral reefs, and shell-forming organisms, some of which are already under threat from climate change and pollution. Salt sedimentation also impacts the ocean in unexpected ways. When salts and minerals precipitate out and settle on the ocean floor, they can accumulate as valuable mineral resources, such as manganese nodules and other metal-rich sediments. These minerals are of interest for deep-sea mining, which could become a major industry in the coming decades. However, mining these resources could disturb sensitive seafloor ecosystems, with potential repercussions for marine biodiversity. The delicate balance of minerals on the ocean floor helps regulate water chemistry, and any disruption to this balance could have long-term impacts on ocean currents and, subsequently, global climate. On the flip side, the formation of salt deserts, or salt domes, at the seafloor can create dead zones, environments too harsh for most marine life to survive. Salt domes occur when vast quantities of salt accumulate in isolated areas, impacting the surrounding marine ecosystems by creating zones with minimal oxygen and altered pH levels. This creates challenges for species that rely on oxygenated waters and can disrupt food chains. So, will the oceans get saltier over time? The answer is complex. On one hand, the continuous input of salts suggests they could, but sedimentation and biological processes, such as shell building by organisms like corals, naturally remove some salts from circulation. Even if global temperatures continue to rise, causing increased evaporation, the rate of change in ocean salinity would likely be gradual, taking thousands to millions of years to become significantly noticeable on a global scale. In summary, the ocean's salinity is a finely tuned balance, maintained by processes that have been active for millions of years. From rivers and hydrothermal vents to sedimentation and evaporation, the ocean remains in dynamic equilibrium, shaping a habitat capable of supporting diverse marine life. The salts in the sea are not just a random byproduct, they are essential to life and climate stability, creating a world in which all marine organisms, and we, can thrive. Understanding this balance is not only important for ocean science but for recognizing the subtle ways our planet's systems work in harmony to sustain life.